Machine learning, big data, and the internet are three words that started a revolution in the AI space. In today's episode of our journey from Turing to AGI, we'll delve deep into some advances that machine learning brought to the field of AI. But before we jump into today's topic, we've launched a new newsletter covering what's happening in AI, plus some bonus content. Stick around until the end of the video to find out how to access it. Right, now back to today's video. Machine learning is a maze with interesting branches that continuously leads to more interesting parts of artificial intelligence. One branch of AI linked to machine learning that has garnered a lot of attention lately are neural networks. What really are neural networks? Basically, neural networks try to mimic the human brain. It's the method of artificial intelligence that allows computers to learn from data, similar to how a human would. This process, where the computer learns to function like a brain, is a deeper and sophisticated type of machine learning known as deep learning. Now, before we dive into deep learning, let's keep our focus on the neural networks and how they work. So how do neural networks function? They use interconnected nodes which mimic the biological neurons in the human brain. These nodes are arranged in a way that looks like the human brain. So basically, they're arranged in a layered structure just like the brain. Now, with neural networks, the system creates an adaptive process that allows the computer to continuously learn and improve from experience. As a result, neural networks try to solve some complicated problems such as summarizing documents and recognizing faces. They also carry out these functions with a very significant level of accuracy. Meanwhile, neural networks may look like a groundbreaking product of machine learning, but it has not been spared from its own fair share of ups and downs. The idea of an artificial neural network took root in the mind of AI researchers as early as the 1940s. It's also one that's fascinated and kept the scientific community excited for decades. I mean, the possibility of creating mathematical models which basically contain artificial neurons that mimic biological neural networks is enough to give a scientist the chills. Plus, the prospect of seeing this magnificent network solve problems related to several fields of technology like computer science, electronic simulation, and others. Now let's journey through time and go through some high points in the development of these artificial networks. Before 1959, neural networks existed mostly in theory, gracing the pages of scholarly journals. The theory had no real-life application, hence it was an untested idea until two Stanford researchers came into the picture. Bernard Widrow and Marcian Hoff developed models known as MADALINE and ADALINE. ADALINE was a system trained to recognize binary patterns. It was developed in such a way that if it was reading something like streaming bits from a phone line, it could predict the next bit accurately. On the other hand, MADALINE was actually the first neural network applied to real-life problems. The MADALINE system uses an adaptive filter to eliminate echoes on phone lines. Interestingly, while this system may be quite old, even as old as air traffic control systems, it's still in commercial use. Now, this initial success of neural networks was followed by others, however. It was cut short after some time and was eventually left behind. But how did this happen? Well, traditional system architectures like the von Neumann architecture found their way into computing and were widely adopted. So, neural research fell off the radar, and over time everything grew cold. Neural research was frozen in time for a while, and this is despite some positive suggestions about the system by von Neumann himself, the creator of the system that led to its demise. Von Neumann at some point even suggested that the system can imitate the neural functions by using telegraph relays and vacuum tubes. By 1969, the shift away from neural networks was already strengthened. Two scientists, Marvin Minsky and Seymour Papert, added their voice to this line of thought in their article titled Perceptrons. In this paper, the duo argued that neural networks were inadequate to solve real problems. In fact, they claimed that neural networks were useless when it came to practical applications, so they practically died and were buried among the antiques and relics of time. After decades of neglect and gathering dust, interest in neural networks was renewed and the idea clawed its way back into the consciousness of researchers. It all started in 1982 when John Hopfield, a researcher in Caltech, presented a paper to the National Academy of Sciences. You see, prior to 1982, the prevailing idea amongst researchers was that neural networks should be connected in one direction. However, Hopfield shattered this approach by suggesting the creation of neural networks and machines generally using bidirectional lines. While Hopfield's idea appeared novel, someone else came along to move the idea further. In that same year, two scientists, Riley and Cooper, developed a hybrid network. This network was essentially a system with multiple layers, and each of the layers used a different problem-solving strategy. So, neural networks moved from rudimentary to almost advanced levels in a space of a year. 1982 would go down as the golden year for neural networks, because in that same year, the US and Japan held a joint conference on cooperative and competitive neural networks. While there was some camaraderie between the two nations, Japan would eventually make an announcement that would shake the United States. So, after the joint conference, Japan announced that it would take a quantum leap to the fifth-generation effort on the development of neural networks. This announcement rattled both US researchers and financiers because it looked like Japan was leaving them behind in the field of AI. Now, because of the reality of being left behind, the financiers and institutions provided more funding for AI research. Now, with funding in place, researchers tested out new things and tried to improve on the old. In 1986, the idea of multiple-layered neural networks gained traction and was in the news, but there was just one problem. Scientists were at a loss on how to extend the Widrow-Hoff rule to multiple layers. So to achieve this, 3 independent groups of researchers took up the challenge. Eventually, each of the teams independently came up with similar solutions, including a team that had a former member of Stanford's psychology department, David Rumelhart. So what was the solution they discovered? Their ideas form the basis of what's now called backpropagation. This basically means that this system distributes pattern recognition errors throughout the network. And unlike the hybrid networks that use just 2 layers, this network uses many layers. As a result, backpropagation networks are slow learners, meaning that they need thousands of iterations to learn, as opposed to the symbolic models employed by earlier hands in AI like McCarthy, Newell, and many others. Backpropagation gave researchers an alternative approach. This model was also able to explain the function of the mind. As a result, the models based on a more than alternative connectionist approach were eventually seen as complementary to those using a symbolic approach. Note that all these advances in the development of neural networks were done during the AI winter. It looked like researchers took some time off during the winter to rethink their strategies, and it yielded great results, such that in the end, this approach laid the foundation for the rebirth of neural networks. It also became the groundwork for the emergence of more advanced forms of machine learning, such as deep learning in the late 1990s and 2000s. Speaking of deep learning, the 2010s were iconic for the field of artificial intelligence because they heralded the beginning of the deep learning renaissance. This turn of events took the capabilities of artificial intelligence to a whole new level because it brought about transformative advancements and unprecedented capabilities. Now, this renaissance coincided with some advancements in the 2010s that led to huge progress in various areas of artificial intelligence. Advances such as an increase in computational power, the availability of massive datasets, and some significant improvements in algorithms, when coupled with deep learning, produced massive results in various areas. Image and speech recognition, natural language processing, and reinforcement learning all saw remarkable progress thanks to this marriage of events. Now, let's explore some of the events that marked this renaissance. Image recognition, before 2012, was heavily reliant on the ImageNet Large-Scale Visual Recognition Challenge, or the ILS-VRC. But in 2012, a group of AI researchers made a discovery that blew things up. The group, which includes Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton, developed a deep learning model called the AlexNet. Now, AlexNet was a significant upgrade from the ILS-VRC. In fact, it beat the old system by a very significant margin. So what was AlexNet all about? Well, basically, AlexNet is a convolutional neural network, or CNN, and this deep learning system opened up image recognition to a whole new level. As a result of its success, there was a renewed interest in AI research. CNNs like AlexNet have since become the staple when it comes to the development of computer vision. This has birthed the rise of a whole lot of applications such as facial recognition, autonomous vehicles, and finally improvement in medical image analysis. Beyond CNNs, deep learning also revolutionized natural language processing, or NLPs, during this time. There was also the rise of some other neural networks developed particularly in the 1990s during this period too. One such neural network was the long short-term memory, or LSTM, a recurrent neural network developed by Sepp Hochreiter and Jürgen Schmidhuber. LSTM was particularly popular because of its ability to model sequential data like speech and text. While LSTM was a major upgrade, in 2013 Google took things a notch higher with its speech recognition system. Now, this speech recognition system was powered by deep learning, and it improved the accuracy of voice commands and transcription beyond where LSTM left it. Still in the decade of the 2010s, AI researchers developed some more advanced transformer-based models. Some of these models, like Google's BERT and OpenAI's GPT, took NLP tasks to levels never seen before. These models have since led to advancements in machine translation, sentiment analysis, and text generation. These advancements have produced mind-blowing results such as making AI able to understand and generate human-like text. Now, another subfield of AI that felt the effect of the Renaissance was reinforcement learning. This branch of AI basically focuses on training agents to make decisions in complex environments. So Google acquired a British AI company, DeepMind, and in 2016, it developed a Go playing system known as the AlphaGo. The AlphaGo AI was so powerful that it defeated the world champion Go player Lee Sedol in a 5-game match. This victory was a turning point in AI research because it showed the potential of deep reinforcement learning, especially with its ability to tackle complex strategic tasks. The deep learning renaissance also spread its tentacles further afield to the development of autonomous vehicles and advanced robotics. Self-driving cars became a reality thanks to this effect, and companies like Tesla and Waymo were at the forefront of this advancement. They integrated AI systems into their vehicles, giving them the ability to navigate unaided and make decisions in complex situations. On the other hand, Boston Dynamics made remarkable progress in robotics. They created intelligent humanoid and quadruped robots like Atlas and Spot that are so advanced they can navigate complex terrains and perform several tasks with mind-blowing dexterity and autonomy. In the end, the deep learning renaissance pushed the frontiers of AI development farther, and it did so rapidly. But another cluster of events added speed to the AI trajectory by making deep learning easily accessible. In November 2015, the Google Brain team released a platform known as TensorFlow. This platform is a vast collection of tools, libraries, and resources that enable seamless deep learning model building and deployment. This release was followed with rapid fire by the Facebook AI Research Lab that released PyTorch in October 2016. Just like TensorFlow, PyTorch was also a deep learning platform. Now, what's the thread that connects these two events? Well, one would think there was a competition of sorts. That's not really the case here. Google Brain and Facebook AI Research Lab both made deep learning open source. These two platforms were developed to provide every researcher or programmer who cares an enabling environment to work with deep learning tools, and boy, from that point, AI development has grown faster than ever. Open source AI platforms were not limited to these two others, like Kira, Apache MaxNet, TF-Learn's, Theranos have also sprung up. So the next direction of the AI train, moving from Turing to the ultimate destination, AGI would test the waters of full democratization. The results of this move is already visible in the rate at which AI has developed and will develop in the past few years. Want to see where this is taking AI? Join me in the next episode. But for now, it's over to you. How do you think open source AI will influence its development going forward? Drop your thoughts in the comment section below. Don't also forget to hit the subscribe button and stay tuned to Tectonic Shift for more exciting AI content. If you made it to the end, we've launched a new newsletter. The weekly newsletter covers all the new and exciting things happening in AI and highlights the latest tools and plugins we hear about. As a major bonus, those who sign up today will get a 5-part mini AI chatbot prompting course. We've been using AI since before it came out and have learnt through trial and error the most effective ways to prompt. By using our methods and secrets, you can become 32 times more effective at prompting and getting the result you want. Check out the link in the description. Until the next episode, bye for now.